code-compliant way is to connect the number 6 copper to the equipment grounding conductor, or EG. According to the National Electrical Code, or NEC section 250.4. A2, the equipment grounding conductor shall be connected to the grounding electrode system as close to the point where it enters the building as practicable. In the case of a pole light, the number 6 copper is the grounding electrode conductor, or GEC, which is the conductor that connects the equipment grounding conductor to the grounding electrode system. The EGC is the conductor that provides the path for fault current to flow to the grounding electrode system. Therefore, in order to ensure that the grounding electrode system is effective, the number 6 copper must be connected to the EGC as close to the point where it enters the building as practicable. Let's delve a bit deeper into the components mentioned and their roles within the electrical grounding system. Firstly, the grounding electrode conductor, or GEC, serves as the critical link between the equipment grounding system and the grounding electrode. The grounding electrode, typically a ground rod, metal water pipe, or other approved grounding element, is physically embedded in the earth to provide a direct connection to ground potential. The GEC purpose is to establish a low impedance path from the equipment grounding system to this grounding electrode, ensuring that any fault current can safely dissipate into the earth. The size of the GEC is determined by NEC Table 250.66 based on the size of the unrounded service conductors. Secondly, the equipment grounding conductor, or EG, plays a crucial role in providing a low impedance path for fault current to return to the source, typically the service equipment or separately derived system. The EGC is connected to the non-current carrying metal parts of electrical equipment, such as enclosures, raceways, and motor frames, ensuring that these parts are at or near ground potential. In the event of a ground fault, where a live conductor comes into contact with the metal enclosure, the EGC provides a path for the fault current to flow back to the source, tripping the overcurrent protective device, such as the circuit breaker or fuse, and energizing the circuit. The size of the EGC is determined by NEC Table 250.122, based on the rating of the overcurrent protective device protecting the circuit. NEC Section 250.4. A2 emphasizes the importance of connecting the GEC to the grounding electrode system as close as practicable to the point where it enters the building. This requirement aims to minimize the impedance of the grounding path, ensuring that fault current can flow quickly and effectively to the grounding electrode. A longer GEC run introduces more impedance, which can impede the flow of fault current and delay the tripping of the overcurrent protective device. This delay can increase the risk of electrical shock or fire. In the specific case of a pole light, the pole itself is considered part of the equipment enclosure and must be properly grounded. The number 6 copper conductor serves as the GEC connecting the pole's grounding terminal to the grounding electrode, typically a ground rod driven into the earth near the base of the pole. The EG, which runs with the circuit conductor supplying power to the pole light, is connected to the metal pole and also to the GEC at a junction point within the pole. This connection ensures that the pole is effectively grounded and the fault current can quickly flow back to the source. Connecting the number 6 copper directly to a mechanical lug mounted inside the pole without connecting it to the EGC is not code compliant. This method does not provide a low impedance path for fault current to return to the source, and it can compromise the effectiveness of the grounding system. The mechanical lug only provides a connection to the ground rod, but it does not ensure that the metal parts of the pole are properly grounded. Therefore, it is essential to connect the number 6 copper to the EGC within the pole to ensure that the grounding system is code compliant and effective. To further clarify, let's consider the potential consequences of an improperly grounded pole light. If a live conductor inside the pole comes into contact with the metal enclosure and the pole is not properly grounded, the metal enclosure will become energized. Anyone who touches the energized pole could receive an electrical shock. If the pole is properly grounded, the fault current will flow through the EGC back to the source, tripping the overcurrent protective device and energizing the circuit. This will prevent the metal enclosure from becoming energized and protect people from electrical shock. In addition to protecting people from electrical shock, proper grounding also helps to protect equipment from damage. When fault current flows through the EGC, it creates a voltage drop along the conductor. This voltage drop can damage sensitive electronic equipment. Proper grounding minimizes the voltage drop, protecting equipment from damage. The NEC provides specific requirements for the installation of grounding electrodes and grounding electrode conductors. These requirements are designed to ensure that the grounding system is effective and safe. Firstly, grounding electrodes must be installed in accordance with NEC section 250.52. This section specifies the types of grounding electrodes that are permitted, such as ground rods, metal water pipes, and concrete encased electrodes. It also specifies the minimum size and length of the grounding electrodes, as well as the requirements for their installation. Secondly, grounding electrode conductors must be installed in accordance with NEC section 250.64. This section specifies the requirements for the size, material, and installation of the GEC. It also specifies the requirements for the connection of the GEC to the grounding electrode into the equipment grounding system. Thirdly, equipment grounding conductors must be installed in accordance with NEC section 250.118. This section specifies the types of conductors that are permitted to be used as EGC, such as copper conductors, aluminum conductors, and metal raceways. It also specifies the requirements for the size and installation of the EGC. The NEC also provides specific requirements for the grounding of specific types of equipment, such as motors, transformers, and generators. These requirements are designed to ensure that the equipment is properly grounded and that fault current can flow safely back to the source. In summary, proper grounding is essential for electrical safety and equipment protection. The NEC provides specific requirements for the installation of grounding electrodes, grounding electrode conductors, and equipment grounding conductors. By following these requirements, electrical systems can be designed and installed to be safe and effective. Now let's discuss some common misconceptions regarding grounding and bonding. One common misconception is that grounding is only necessary for safety. While safety is a primary concern, grounding also plays a critical role in the proper operation of electrical equipment. Grounding provides a stable reference point for voltage, which is essential for the accurate functioning of electronic devices. Without proper grounding, voltage fluctuations can occur, leading to erratic behavior or damage to sensitive equipment. Another misconception is that any connection to earth constitutes proper grounding. Simply sticking a wire into the ground does not guarantee an effective grounding system. The grounding electrode must be of sufficient size and properly installed to provide a low impedance path to ground. Additionally, the grounding electrode conductor must be properly sized and connected to the equipment grounding system. Another misconception is that grounding and bonding are the same thing. Grounding and bonding are related but distinct concepts. Grounding refers to the connection of electrical equipment to the earth, while bonding refers to the connection of non-current carrying metal parts of an electrical system to create a continuous electrical path. Bonding is essential for providing a low impedance path for fault current to flow back to the source, which is necessary for the proper operation of overcurrent protective devices. Another misconception is that ground fault circuit interrupters, or GFCIs, eliminate the need for grounding. GFCIs are designed to protect people from electrical shock by detecting small imbalances in current. While GFCIs provide an important layer of protection, they do not eliminate the need for grounding. Grounding is still necessary to provide a low impedance path for fault current to flow back to the source, which is necessary for the proper operation of overcurrent protective devices and for the protection of equipment. Let's also touch on the importance of regular inspection and maintenance of grounding systems. Grounding systems are subject to corrosion, damage, and degradation over time. Regular inspection and maintenance are essential to ensure that the grounding system remains effective and safe. During an inspection, the following should be checked. Firstly, the grounding electrodes should be inspected for corrosion and damage. If the grounding electrodes are corroded or damaged, they should be replaced. Secondly, the grounding electrode conductors should be inspected for loose connections and damage. Loose connections should be tightened, and damaged conductors should be replaced. Thirdly, the equipment grounding conductor should be inspected for loose connections and damage. Loose connections should be tightened, and damaged conductors should be replaced. Fourthly, the resistance of the grounding system should be measured to ensure that it is within acceptable limits. A high resistance indicates a problem with the grounding system, such as a corroded grounding electrode or a loose connection. If the resistance is too high, the problem should be identified and corrected. In addition to regular inspections, grounding systems should also be maintained. Maintenance activities may include cleaning grounding electrodes, tightening connections, and replacing damaged conductors. Proper documentation of grounding system inspections and maintenance is also important. This documentation should include the date of the inspection, the findings of the inspection, and any corrective actions taken. This documentation can be used to track the performance of the grounding system over time and to identify potential problems before they become serious. To further enhance understanding, let's consider some practical examples of grounding applications. In a residential setting, the electrical panel is typically grounded to a ground rod or a metal water pipe. All of the circuits in the house are then grounded back to the electrical panel through the equipment grounding conductors. This ensures that all of the metal parts of electrical appliances and equipment are at or near ground potential, protecting people from electrical shock. In a commercial setting, grounding is even more critical due to the high voltages and currents involved. Commercial buildings often have complex grounding systems that include multiple grounding electrodes, grounding electrode conductors, and equipment grounding conductors. These systems are designed to protect people and equipment from electrical shock and fire. In an industrial setting, grounding is essential for the safe operation of heavy machinery and equipment. Industrial facilities often have extensive grounding systems that include grounding grids, which are networks of interconnected grounding conductors buried in the ground. These grounding grids provide a low impedance path for fault current to flow back to the source, protecting people and equipment from electrical shock and damage. The proper design, installation, and maintenance of grounding systems are essential for ensuring electrical safety and equipment protection. By following the requirements of the NEC and adhering to best practices, electrical systems can be designed and installed to be safe, effective, and reliable. Remember to always consult with a qualified electrician for any electrical work to ensure that it is done safely and in accordance with the applicable codes and standards.